Okay, we are going to get started. Hi, everyone. Welcome to today's Safer Sim webinar. And today we have three researchers from the University of Central Florida. They are going to be discussing their research project that was focused on utilizing micro simulation to evaluate the safety and efficiency of the expressway system. So I will let Mohamed take over from here.
Good afternoon. This is Mohamed Abdel-Aty, professor with the University of Central Florida, along with two of my colleagues, Dr. Ling Wang and Dr. Jaeyoung Lee. This work was funded by Safer Sim, and it is related mostly to the PhD dissertation of Dr. Ling Wang. It builds on our ongoing research of real-time crash risk evaluation and prediction that we have started a few years ago. We are basically, sorry about this, I was playing with the laptop, so apologies. So we have basically been looking into real-time data, which is basically the data that we get from microwave detectors or other type of detectors to evaluate in real time the turbulence and the increase in risk on roadways. You know that microsimulation do not really represent accidents, but microsimulation is a good tool to investigate surrogate measures of safety, such as the crash risk indicators that we get from the real-time data, as well as using programs such as SSAM with microsimulation to determine the conflicts. This particular research, as I said, is part of a PhD dissertation, and in this particular research we are looking into the different types of segments on expressways and freeways, such as merge and diverge, and also the weaving segments, in addition, of course, to the basic freeway segments. So you can see here the potential conflicts in the different types of segments, and we'll elaborate on that in a minute. You might recall from the highway capacity manual, there are three types of weaving. Here we are talking about, in particular, ramp related weaving, which therefore we are focusing here on types A and B. Type A is one lane change for each of the two weaving volumes. Type B, one weaving without a lane change, and the other at most one lane change. And you can see it again here, type B. The other topic related to safety that we touched on in this work is the type of analysis. You know that the majority of safety research and the traditional type of safety performance functions aim at predicting the frequency of crashes in a time period, say a year or more than 1 year. And therefore, these functions use the average daily traffic or the annual average daily traffic. We think from our experience that this is, although this is, well documented and it forms the core of the highway safety manual, we think that this is not very accurate, particularly since we are getting much more refined and better data. So in this particular research, we have also looked at hourly crash prediction, as well as what we call real-time safety analysis, which is determining the risk in real time, maybe at a 5-minute period of crashes. And with respect to the real-time safety analysis, we are interested in looking at the flow parameters immediately before a crash. So for example, this figure shows a drop in speed, for example, after the crash, but what was happening before the crash is one of our parameters of interest. Whether this period was disruptive, and how can we measure it, and how can we relate it to actual crashes, etc. Also, I touched at the beginning on the surrogate safety assessment model, SSAM, which is it's a conflict-based model looking at the trajectory of vehicles in the micro simulation, and therefore determine whether this could be considered a close miss or a potential conflict, and therefore we would be able when we feed the micro simulation into SSAM to be able also to get measures of safety, which is a welcome development, of course. The other issue that we want to get into also is the active traffic management, and how can, since we are dealing with real-time crash analysis, how this could be mitigated in real time. And of course, there are multiple active traffic management strategies, or multiple ITS type strategies that we can implement in real time to mitigate the increase in risk. And for example, the variable speed limits and the ramp metering and other measures could be applied once we detect a problem in real time. So these are some of the objectives of this current research, looking at the different segment types, also evaluating the type of safety analysis that would produce the best and most accurate results. Also look at the different types of crashes at segments that we consider of high risk, in addition to the simulation part, which is VISSIM and SSAM, and then implementing the active traffic management strategies in the simulation in order to improve the increase in risk. The study area is the Central Florida Expressway network, and it has actually 5 roads, but we are representing here only the 3 major ones that has the majority of the traffic. We also have data from the DOT RCI database that give us the geometry, etc. We also have the weather data from NOAA and other sources, such as the airport weather stations that are close to the network, so that we know also the real-time weather data. The traffic data is very extensive on this network. We have microwave vehicle detection systems and other systems, but in this particular study, we use the MVDS, which give us a minute-by-minute, lane-by-lane volume and speed and lane occupancy at a spacing of about 1 mile, Ling?
0.5 miles.
0.5 miles, about 0.5 miles. And also we have the crash database, so we know also where crashes happened, when exactly they happened, and therefore we can identify the traffic parameters leading to the crashes. The data used, we have used in the study 247 segments from the 3 expressways, as I mentioned, that they represent the merge, diverge, weaving, and basic segments. We have developed crash prediction models, as I explained, on the 3 levels. The daily type models, which is the typical SPFs. We use the Poisson log normal, Bayesian Poisson log normal, which is typical. We also use Poisson multinomial for the hourly crash prediction, and in this case we are looking more at the hour-based traffic, as well as the crashes by time of day, looking at the crashes at the specific hour. And then we looked at the real-time crash prediction using a multinomial, again Bayesian multi-level logistic regression, and we use the case control design because in this particular part of the analysis we are interested to look at normal situations versus crash inducing situations. So it is a 0-1 type situation, and that's why we needed control locations where crashes did not occur or the traffic was normal. Quickly looking at the characteristics of the different segments, the 4 segments that we talked about, the merge, diverge, weaving, and basic, looking at the crash history over about 2 years, and looking at the type of crashes and the crash rates, you can see that clearly the diverge and the weaving section have a higher percentage of rear end crashes, but also they have higher rates of crashes. So this indicates we need to focus more and understand the problems with these particular locations. Here are results of the three models. ADT based model, which is a daily based model. So we're basically aggregating the data, for example, the volume, which is a typical exposure measure based on the sensors at every segment. So again, we are not only using here like the measured ADT, but we are actually calculating the ADT based on the sensors for every segment and aggregating it for a day. And then looking at the hourly based, where we are aggregating the traffic from the sensors for 1 hour and relating it to the crashes that happened at the same hour. And then looking at the real time, which is the volume at a 5 minutes interval preceding the historical crashes. In the ADT based and the hourly based speeds, we would be forced to look at the speed limit, which is posted on the different segments. However, in the real-time analysis, we can actually look at the actual speed that happened in the 5 minutes preceding the crash. So that's why you see difference in the significant variables between the three models. We looked at the truck percentages, the number of lanes in the segment. We looked at the segment length, whether it was a dummy representing whether it was a weaving segment or a diverge segment. What you can see here is that in most or all models, you can see the exposure or the log of the volume is significant. You can see that the speed has a negative effect, and this probably is due to congestion. As the number of vehicles increase, the speed goes down. But not all the variables appeared in all the models, and this is another also factor to consider when we are comparing between the different models. But models have indicated that the weaving segment is relatively more dangerous than the other types of segments, and only the hourly based model showed that the diverge segment also has a higher risk than the other types of segments. Ling, do you want to add something here explaining the model? So the weaving, I think I explained it.
Yeah.
Do you want to add something here, Ling?
No, I'm good.
You are good?
Yeah.
Okay. Don't worry, I'll give you time to speak. Just, when I get started, sometimes it's difficult to stop, but it's interesting work, that's why. All right. So to answer the question, which model or which is the best way to represent crashes on freeways? And we looked at the hourly, the daily, and the real time, as you saw. And just to give you, more information, if you're looking at a daily based crash frequency model, basically you have one period. It's a 1 day, one observation. If you're looking at the hourly, you have a 24-hour representation for the day. If you have a 5-minute interval, which is what we use in that extreme disaggregate analysis in the real time, then we're talking about 24 hours at 884 days for the study period that we studied, and 12 intervals per hour, which represent 5 minutes by 12 is 60 minutes basically. So you see that we are looking at much more refined data at a 5 minutes interval, but the data allow us to do that, and this is the good thing about the current research in big data and analytics is that the sensing technologies that we have on our roadways and looking at data for longer time periods, we are able to handle this data. And again, I am kind of questioning the going back and looking at ADT based analysis, but maybe this is not the topic in today's presentation. It is possible to compare the daily and the hourly models by several measures, including the mean absolute deviation. However, for the real-time crash risk, we are looking at the area under the curve, or the ROC, to evaluate how the model is doing. So actually, we have apples and oranges here when we compare the models. So it is easy for us to compare the daily and the hourly crash frequency model, and you can see here apparently the error is much less in the hourly model, which makes sense, of course, because we are not just regressing all the crashes to one value, or the ADT. We are looking at the specific volume in the hour that was responsible for the crash that happened in this particular hour. When we are looking at the real time, you can see that ROC is superior, and again, because we are extremely disaggregate and looking at the specific 5-minute characteristics that caused the historical crashes. If we represent this over the hour and the crash frequency chart, and you look, for example, at of course, we know that the volume of traffic changes over day, and we have the typical 2 peaks in the morning peak hour and the afternoon peak hour, and you can see crashes kind of follow the same pattern. I'm not talking here about crash severity, I'm talking about just the crashes. When you have probably during peak hours a lot of fender bender type crashes, because there are more interaction and stop and go during peak hours, but in general crashes, you can see the field hourly crashes, which is the dark line, kind of follow the same pattern morning and afternoon peak. And you can see that the hourly model, the output of the hourly crash model, kind of very similar and very close. So the hourly model definitely do much better than the daily model, which is represented by the red horizontal straight line, which doesn't tell us much. It does not give us much about the differences within the day and based on the specific volume. The aggregation of the results of the 5-minute based real-time crash risk estimation also is reasonable, however, does not do as well, slightly underrepresented the crashes, I would say, and this might be an interesting point for further research, why it is underestimating the distribution of crashes. Now going into looking at the real-time analysis and specifically for weaving segments. So from this part of the study, we have identified that weaving sections has issues, and we need to now start to zoom in and develop models for the weaving sections to see the pattern of crashes and how we can in real time improve the situation. And I think it might be a good time to that Dr. Ling Wang talk a little bit more about her research. Ling?
Okay. So for the real-time safety analysis for weaving segment, and we used the logistic regression model. And the study subject is 16 weaving segment on the State Road 408. The reason why we choose 408 is because this one across the downtown area, so a lot of on-ramp is closely followed by the off-ramp, so a lot of weaving segment. For this one, the study period is 21 months. And for the data connected is for the crash, traffic, geometry, and the weather. Because for the real-time safety analysis, we will compare the crash and the non-crash observations. The number of non-crash observations actually is much more than the crash observations. So we adapted the case control design to provide a valid estimation of variables impacts on crash odds ratio. So this one is the real-time crash analysis model. And from this model, you can find that when the coefficient is more than 0, it means the increase of this variable will increase the crash risk. And because this one is based on the case control design, so we cannot get the actual crash likelihood, but we can get the odds ratio. So this one shows the odds ratio formula. When the odds ratio is more than 1, actually it means the condition 2 is more danger than the condition 1. And if the odds ratio is equal to 1, means the two conditions have the same safety. And if the odds ratio is less than 1, means the condition 1 is more danger than condition 2. From the model, let's go back to the model. From the model, you can find the speed difference in the viewing inference length has positive impact on the crash likelihood. That means when the speed difference, when the beginning of the speed at the beginning of the viewing segment is higher than the end of the viewing segment, the crash risk will be high. So we were wondering whether we can use the variable speed limit to decrease the speed difference and then to improve the safety. And the other one is the viewing inference length. This one, the model is provided by the HCM 2010. It estimates how what's the distance be impacted by the viewing. And the most important variable is the viewing ratio. It calculates the viewing volume over the total volume. At that time, we were thinking whether we can use the ramp metering to reduce the all ramp volume and then to reduce the viewing ratio to further increase the safety. So that is the reason why we choose variable speed limit and ramp metering in the future, in the later study. And we need to pick up the one of the most dangerous viewing segments in the network. We found that during peak hours, the mileposts between 12 to 14, there is a viewing segment. And for this viewing segment, in a year I checked, there were 8 crashes happened. So we built a simulation network according to this viewing segment. The simulation time is 6:30 to 10:30, and during the simulation time, there were 2 peak hours. And the geometrical characteristic of the simulation network is the same as the field, including the lane width, number of lanes, divergent and merge locations, etc. And the traffic data is from the microwave vehicle detection system. We aggregate the traffic volume into 15 minutes to capture the dynamic of the traffic. And for the designed speed distribution, we choose the off-peak hour during the day to find what is the design speed the drivers want to achieve. From the simulation, we run it for 10 runs with different random set, and the result shows the simulation is well calibrated. The average GAH is 1.97, and the 96.4% of the observations, the volume are highly consistent with the field, and the network is also well validated. The speed of the simulation is also consistent with the field. As what I mentioned from the crash mechanism of the viewing segment, we found the ramp metering and variable speed limit can improve the safety of viewing segment. So we proposed a ramp metering. Previously, the ramp metering are only based on the operation of the segment. But actually, if we want to improve the safety of viewing segment, if we want to improve the safety of the main line, we need to consider the safety of the main line. So we add one more item, and this item is used to consider the safety. When the safety of the viewing segment is not good, we will use this item to decrease the number of vehicles enter the main line. And if the safety is good, we will increase the ramp metering rate. And based on the ramp metering rate, we can calculate the green time of the signal. But usually, because if we only consider the occupancy and also consider about safety, sometimes the vehicle will pile up on all ramps, so it will result in a lot of delays. So we add the queue control when the queue of the viewing segment is more than 10. We will increase the green time. In addition to ramp metering, we also have the variable speed limit. When the crash risk is higher than the critical crash risk, the variable speed limit at the beginning and the end of the viewing segment are activated to reduce the speed difference between the beginning and the end. Additionally, we also consider the integrated strategy. This one have ramp metering and also variable speed limit. For this strategy, the ramp metering is always active, but when the queue is more than 10 vehicles, if you remember clearly, when the queue is more than 10 vehicles, the green phase of the signal will be increased. That means more vehicle will enter the viewing segment, but maybe the vehicle will drive at very high speed, so they cannot find enough gaps. So at that time, the variable speed limit is activated to reduce the speed limit on the main line to provide more gaps for ramp vehicles. And all the active traffic management is conducted in the microscopic simulation VISSIM through the call interface. This one is the network we build in the VISSIM. You can see the ramp metering is installed at the end of the on-ramp, and the variable speed limit is installed at the beginning or at the upstream and the downstream of viewing segment. In total, we have 13 scenarios. For the case 1 is the base condition. We do not have any active traffic management. For the case 2 to 4, we have 3 ramp meterings. The first, the case 2 is for the traditional ramp metering. The case 3 is the ramp metering, but we do not add the queue control. But for the case 4, we add the queue control. For the case 5 to 12, we have these are the variable speed limit. We have different options. The variable speed limit is installed at the upstream, or installed at the downstream, or installed at the both. For the number 13 case, we integrated the ramp metering and the variable speed limit together. So this one is before the application of the active traffic management. We can find that after about 16 minutes, the conditional crash risk of the viewing segment is very high, and you can find the high risk in red color. But after we apply the ramp metering and the variable speed limit together, you can find the odds ratio. The previous odds ratio, that one is the blue line. After apply the ATM, you can find the odds ratio is significantly lower than 1. That means the safety is improved a lot. This one is used to show the safety impact of the active traffic management. So from here, you can find the proposed ramp metering is better than the traditional ramp metering. For the traditional ramp metering, you can find the odds ratio actually didn't change much. It's 1.01. It's not significant from 1. But for the ramp metering, the one we proposed, you found the queue controlled ramp metering, actually the odds ratio is 0.92. That means this strategy improved the safety by 8%. And also for the non-control ramp metering, you can find the average travel time actually increased a lot, because it didn't consider the vehicles on the on-ramp, and the vehicles pile up on there. But after we add the Q control, the average travel time is decreased significantly, but still a little bit higher than the base condition. For the variable speed limit, we found the upstream speed limit actually is more effective than the downstream speed limit, because after the downstream, the vehicles has already been in very low speed. Even if you increase the speed limit, it cannot be, the vehicle cannot accelerate immediately. So it's recommended that to put a variable speed limit at the upstream of the viewing segment. And also we found the 45 miles per hour speed limit was much better than the 50 miles per hour speed limit, because the more you reduce the speed limit at the beginning, at the upstream of viewing segment, the lower speed at the beginning of viewing segment is, and the speed difference of the viewing segment will be much lower. So the safety of the viewing segment will be improved. For the best scenarios of the ramp metering variable speed limit and the integrated one, we found that the variable speed limit actually it improved the safety more, because for the integrated one, the variable speed limit is not always active. It's just active when the Q is more than 10. But the variable speed limit, according to the researchers, and they said always have the compliance issue. The drivers maybe not obey to the new variable speed limit. So under this condition, the integrated ramp metering and variable speed limit is strongly recommended, because even the variable speed limit fails, the ramp metering can also work to improve the safety. We also compared the conflict. The conflict, what Dr. Aty mentioned, is identified by the SSAM, and also the odds ratio. We found that these two are highly correlated. That means the safety of the VISSIM, the safety of the simulated network actually is consistent with the field one, because the odds ratio is based on the field crash risk estimation model. This is our results and the conclusions. First, which segment type is the most dangerous one? The model shows the viewing segment is the most dangerous segment type. This one is it's easy to understand, because for the viewing segment, the vehicles have to merge, to diverge, and to weave in very limited space. So that one is the most dangerous. From the descriptive analysis, we found the rear-end crashes are more likely to happen on the weaving and the diverge segment. In the rear-end crashes actually for the whole expressway system account more than 40% of the total crashes. So if the rear-end crashes in the weaving and the diverge segment, and also for other segments, this type of segment can be, this type of crashes can be reduced, then the whole safety of the expressway system can be improved. In the later, we explored which safety analysis can provide the most accurate result. We found that for the crash frequency analysis, it's better to use the hourly crash prediction, even for the total crash frequency estimation, and also for the hourly crash estimation. But for the real-time safety analysis, we recommend the crash likelihood estimation, because this one can provide more accurate crash likelihood than the other two aggregated ones. For the crash mechanism of the most dangerous segment, we found the configuration impacts the viewing segment type. Actually, for the HCM 2000, the type B viewing segment is strongly recommended, because this one can provide much higher capacity, because one of the weaving action, there is no need for them to change lane. But from this study, we found that the type A viewing segment, that one needs the weaving and diverge, weaving and merge and diverge the actions, both the need to change one lane. So for the traffic operation and safety, maybe sometimes there are not always consistent. We cannot follow everything from the operation. We need to dig more for the safety by ourselves. The crash mechanism also shows that the speed difference between the beginning and the end of viewing segment has a positive effect on crash likelihood, and the maximum inference length is more important than the physical length. Previous study for the viewing segment, the safety, the majority of them use the physical length, but here we found that actually the maximum inference length is more important. Later, we built a VISSIM network. The geometric design and traffic of the simulation network is consistent with the field, and the network is calibrated and validated from both the traffic and the safety aspects. For the active traffic management, it improves that the strategies we proposed improve the safety a lot. The proposed ramp metering is much better than the traditional ramp metering. It reduced the conflict number and also reduced the odds ratio. For the variable speed limit, we found that the upstream variable speed limit is more effective than the downstream variable speed limit, and also the 45 miles per hour speed limit is better than the 50 miles per hour speed limit. Also, we integrated the ramp metering and variable speed limit, and we found that this integrated one enhanced safety more than the ramp metering alone. Based on the study, we have two papers. One is submitted to the AAP, and the other one has been accepted by the TRR. And also, we did the presentations about these two papers in this year TRB, and we from the attendance, and we found that the studies are very good, and also the thinking it is very useful. Okay, thank you. That's all.
Thank you, Ling, very much. If there are any questions, we'll be happy to take them in typing or voice. Jaeyoung, whether there was questions?
No, he said the cannot hear clearly because of the echo, but later it's good. Yeah. Don't typing.
Dawn? Okay.
In this paper, in this.
Thank you, John. That's very kind of you. Thank you. I appreciate the kind words.
Ask what's the next project will be from this result.
What is the next one? Yeah, that's a good question, Don. This is a line of research that we have started many years ago, and we have been looking at all types of road facilities and all kinds of issues using this microscopic level data. And now with the assistance of simulation tools and maybe also driving simulation tools. So I expect us to continue. I mean, these are not the only types of roads. There will be interchanges, there will be toll plazas, there will be other types of roads that we can evaluate based on both real-time data in the field as well as micro simulation, and then to add the human factor aspect, we can take it also to a driving simulation. So for this particular study, I think a natural extension would be to take all these results into the driving simulator and see whether, as Ling mentioned, whether drivers comply with the variable speed limit. Would this improve the situation with respect to driver behavior? So in general terms, the line of research continue with other facilities. Specifically for this particular narrow part of the study, we can take it to the driving simulator and evaluate the effectiveness of variable speed limit and ramp metering on drivers' behavior and therefore safety. Ling or Jaeyoung, do you want to add anything? All right. So they agree with their professor, and so they are good people. You want to take a shot at this? You mean, Don, you mean with respect to accepting or abiding by the variable speed limit? Yes, okay. I think we can draw from other areas in the US, such as Washington State, for example, that has been adopting variable speed limits. And of course, the Europeans, particularly the Netherlands, have a very long experience with respect to variable speed limits. I think we would need to draw from their research and their observation to see how drivers adapt and how long it takes for them to accept and use that and use this advice or these signs.
Thank you.
Yeah, great. Thank you. Of course, yes. Of course, we can share the paper from TRB.
What other road facilities have you used the micro simulation to test the potential interventions?
Yes, yeah. So far, it's mostly freeways and expressways. So we have simulated I-4 before. In the last few years, we have been looking at the expressway network since it's a extensive network, and because one of the keys is the calibration and validation of the simulation network. So we need to use a network that has existing extensive field data, so to enable us to validate and calibrate. So I think the next step is to look at arterials, and this is what we intend. There are limited arterials here or there that have such data. And remember, we are not using aggregate data. We are not using ADTs. We are using microscopic data. So it makes our validation more difficult because we are looking at the 5 minutes measurements. But so far, it's limited access facilities that we have been using.
Okay.
Of course, John. We'll take your email and check with us when you can. Also, in case I lose track, our website as well as the VISSIM website. This group of universities working together on simulation research are already extended their work, and we won the competition last cycle, so we'll be working with each other for at least the next 5 years. So expect more research, more webinars from the 5 universities.
Thank you, John. Thank you for saying this. And we will send you the presentations, and we will also update all the information for the VISSIM website, and also for our own group research group website. And if you have any questions, you can contact us. Thank you.